So finally, we are ready to put together all these ideas to help us understand collisions and what happens when two objects interact. So this is Newton's third law. And Newton's third law says that when two objects collide, the forces they exert on each other is equal in both directions. So equal and opposite. So with these images that I have here, in each case, as one object collides with the other, the force of that collision is equal and opposite in both directions. So let's see if we count the point of contact there, and I'm using these arrows as force arrows, right? So I'm being careful, or trying my best to make them equal in length to show that they are equal in magnitude. And this is true even in situations where the two objects are very different in mass. So here we have a little moon colliding with a large planet, and at the point of impact, the force exerted on each object is equal, equal and opposite. And here we have, let's see, let's call this the point of impact. So this guy running into this guy, and each of them feels the same force of impact. So we could go on and on. It's always the same, equal and opposite. Okay. So we're using the word collision, but I want to be clear that a collision really is any interaction between two objects where they touch, I guess I should say. So here we have a person touching the kitty's chin. So the force that the kitty's chin will feel is equal and opposite to the force that the person's finger will feel from the kitty's chin. All right. So here is an important thing to think about. We've spent time learning that equal and opposite forces cancel each other out, right? Remember those free body diagrams, and wait a minute, isn't the net force here zero because the forces cancel each other out? Well, that's very good of you to think. And here is the difference. That is true when the forces are acting on a single object. So what we learned before is still true. What we're talking about now, though, is a slightly different situation, right? So third law, which is what we're doing now, third law talks about two objects interacting. So just keep that in mind because it's easy to get confused here about what's going on. All right, so two objects interacting. All right, so now we're ready. Let's do this, and let's use Newton's third law to help us understand the acceleration of these two objects after they collide. So the middle panel is where these two very different mass objects collide, and it doesn't even matter like if one is going fast or one is going slow. So whatever speed. And then they collide. So what we've just been saying is that at that point of collision, the forces are equal and opposite. So now we know the force exerted on each object. So going back to Newton's second law, force equals mass times acceleration, we now know the force that is acting on each object as they move away from each other. So let's see, moving away, I'm just going to write that here. I'm trying to avoid using arrows for speed or direction so that our arrows are only for force. Okay, so they're moving away. The big one Well, let's do this. So we have the force value, even if it's just relative for the two objects. So I'm writing the F, and I'm going to use the size of these letters to sort of indicate relative strength. So for the purple object, it's very large, right? So I'm going to make a big M to indicate a big mass, whereas in the red object is much smaller. So I'm going to draw a little m. So we know the forces are equal because that's what third law is telling us. So what must be true of the acceleration of the purple object in order to make these equations have the same f's? So if this is a really big m, we need to multiply it by a very small acceleration in order to have this f equal this f, whereas for the little guy, the acceleration is big. So now, because this one has a big M and a little a, but this one has a little m and a big A, we can cause these two equations to have the same F, because that's what we started with knowing, is that the force that acted on each of them was equal. So we have to play with the magnitude of the acceleration number here because the mass is fixed. We know this one's bigger and we know this one's smaller. So it has to be that the acceleration is different. So little one will move away at a much greater acceleration.